Hello, digital world. Today we're going to talk about visualization of flow past a marine turbine, the information-assisted search for sustainable energy. This project was done by a group of people. Zhenmin Peng, who was a PhD student at Swansea University, Zhao, who also was a PhD student, Michael Nicholas, who was an MRes student at Swansea University, myself, Nick Croft, Rami, Malki, and Ian Masters, who all work in the engineering department at Swansea University, and Chuck Hansen, who is a well-known professor from the University of Utah, who was visiting us at the time we were working on this project. This video voiceover is for David Standingford at zenatech.com and Alison Little at cfms.org.uk. So before we jump into the action, so to speak, I just thought I would give a 60-second-ish background behind the project. So it's pretty clear that renewable energy sources are a much better alternative to fossil fuel energy due to the environmental destruction that fossil fuel-based energy creates. So the MERG group, or the Marine Energy Research Group at Swansea University in the Department of Engineering, studies the development of marine turbines. So marine turbines have some advantages over wind turbines. For example, they can draw a lot more kinetic energy than winds because water is so much more dense than air. And water is a more predictable source of energy than wind, right? The tides are very predictable. And the MERG group works on the development of marine turbines for the Bristol Channel. The Bristol Channel in the UK has the highest gradient of tides in the world for all harbors. The disadvantage of marine turbines, however, is their cost. They're more costly than wind turbines currently, so it makes sense to simulate them or use simulation software before building the real thing and installing them underwater. But simulation data creates lots of challenges because it's so big, right? And that's where visualization comes in. So the Moore group and us work together to create some visualization solutions for their marine energy research. Now, one of the traditional ways to visualize flow is with streamlines. And streamline seeding generally falls into two categories: manual, where the user uses a mouse and manually picks positions in three-dimensional space or maybe four-dimensional space to seed streamlines. That's very slow, painstaking, and error-prone. The other category of seeding streamlines is automatic, where an algorithm seeds the streamlines automatically, maybe uniformly across the space-time domain, or maybe a feature-based approach. What we developed is a so-called knowledge-assisted streamline seeding strategy, which lets the user, in this case the CFD engineer, use their knowledge of the flow directly to seed streamlines in a semi-automatic way. And now we're going to see that in action. So this is what it looks like when a user tries to use the mouse to manually seed streamlines. They're drawing a rake in the space-time domain, and then streamlines are seeded at evenly spaced positions across the rake. And in this case, we're just trying to visualize reverse flow. So reverse flow is destructive to the flow pattern. Right, we want to generate as much kinetic energy downstream as possible. So reverse flow goes against that trend. And we want to minimize the reverse flow. So how can we seed streamlines in areas of reverse flow? Well, it can't be done necessarily in the traditional manual way. So we have developed a visualization system that lets the user see alternative views of the same data, so they can do things like seed streamlines in areas of reverse flow. So we have other views of the data, for example, a parallel coordinates view in the lower left, a spherical histogram view in the upper right, and then a tabular histogram view of the data in the bottom left. And the user can simply brush the x-axis in the parallel coordinates view or the negative velocity axis to see the reverse flow. And this is something that would be very difficult, maybe impossible to do with just a manual seeding technique. And now what we've done is we've turned on something we experimented with, which is distortion, to sort of shrink the lengthwise component of the flow field so we can get a more detailed view of the lateral component of the velocity. And now we can combine brushes in the parallel coordinates view, and we can refine the seeds to one plane in the 3D volume, or multiple planes in the 3D volume. But now we can get a good view of the positions in the 3D domain where reverse flow originates. And once we know that, we can design our marine turbines differently to try to reduce the reverse flow. We can also study the flow past the blades themselves. There's a specific CFD attribute for blade positions, so the user can brush those blade positions in any of the views, but the parallel coordinates view makes sense, and also the tabular histogram view makes sense to brush the positions. And we note that the interaction between all of these views is coordinated. So if the user brushes a region in the parallel coordinates view, all the other views are updated with corresponding selection. So this is the user brushing the position of the blades in the upstream area, the 3 marine turbine blades, and then visualizing the flow that intersects the blades with glyphs, with vector glyphs. Now, to position these vector glyphs manually would be very difficult, maybe even impossible. And this is seeding streamlines from those same positions. So we brush the location of the marine turbine blades, and then we seed streamlines from those positions. And again, it would be very difficult to do something like this with a manual streamline seeding strategy, or even a feature-based streamline seeding strategy, because a customized feature extraction technique would be necessary just for this data set, and that would be very time-consuming and costly. However, a knowledge-assisted streamlined seeding strategy makes the whole task very easy. We can also select the downstream blade in our visualization, just using our knowledge of the CFD simulation data. And that's what the downstream blade looks like. That's the downstream position. And the idea is we don't want to position another marine turbine downstream from the upstream marine turbines that falls in their wake. Here's another view added to the coordinated multiple views of the data in the top right. This is streamlines, a graph of streamlines and their curvature. So the higher the curvature, the higher the location of the point on the graph on the y-axis. And this shows us we can select streamlines or highlight streamlines in that graph with very high curvature, right? And high curvature corresponds to high kinetic energy. And we can actually select individual streamlines in the graph view. For example, we can select the streamline with the most curvature and visualize that. And doing that in a manual with a manual seeding rake would be virtually impossible. It would be difficult but not impossible with a feature-based technique. Okay, that's just a brief overview of the work we did. Thanks to David Standingford of Zenitech.com and Allison Little of CFMS for asking us to create this video. We also want to thank the EPSRC for funding this visualization research. If you'd like to know more details, we're going to post a link to the manuscript, the full manuscript, underneath this video. And if you'd like me to do any more voiceovers of any other videos that we've created, just let me know. Thank you very much.